All right, so tonight we're going to be talking about scheduling tasks, how you determine tasks, how you schedule them, how you determine your costs. These are things which are critical to projects. Without some knowledge about being able to how to do these things, you get into trouble very, very rapidly. So the principal measures of a project are cost or dollars, time, your schedule, and performance. Those are your primary entities associated with a project. For any particular project, one or more of these measures will very likely be constrained in some way, shape. So for example, in this ballooning project that you've got right now, there is a fixed date for the launch. So you have to have your payload ready by this date. So your time is fixed or constrained. You have to be able to adjust your project cost and performance appropriately in order to make that constraint. So your initial estimates of how your project is going to run in terms of cost and schedule um, are going to be required in order for you to figure out whether or not you can actually make that launch date. And after you do those estimates and you find out that you can't, then something has got to happen. All right, you've got to do some trade-off. You've either have to reduce some performance, or you've got to increase the number of people, or you've got to do something. So it's important that you figure out how to do your cost and time schedule efforts immediately, right at the beginning of the program. And once you do that, you also need to monitor that throughout the entire life cycle to make certain that you continue to be on schedule. Did I miss one? Yeah. Okay. Yeah. So the steps, the generalized steps to defining these project tasks are really, in principle, simple. First of all, you have to define your characteristics of your project. We've already talked about some of these things. So your project scope and your project priorities. Remember that scope is derived from your goal, objectives, and requirements. There we go again. All right, there's those little bothersome requirements. They're going to affect how you're going to define your project schedule and tasks. So uh, another reason why you need to get those requirements out of the way and defined as clearly and adequately as you can. Then you need to figure out how to organize the project tasks. Are you going to be organizing your project and your schedule by deliverable, by something that is actually handed over to another a customer or entity, or by a process for how you make phases in your project, or some combination of these two. Um, then you create what's called a work breakdown structure, or a WBS. You'll hear me refer to WBS as many times. That's called the work breakdown structure. That structure is a hierarchical structure of tasks or subtasks. You start off by first identifying your highest level, most general tasks, and then under each one of those general high level tasks, you define your lower level tasks and even lower ones beneath those. So it's a tree structure that goes on. At the lowest level of your WBS are what are called the work packages. These are the entities where you can very easily assign a time and a cost to, and then as you roll up all the work packages through your WBS, you can get a fairly accurate estimate of your time and cost of your project. So again, determining the project scope. Um, this is essential for any sort of effective project plan. What are your objectives? What are your deliverables? What are the outputs over the life of the project? When are these things due? All right. What are your milestones that'll happen during the project? What are your technical requirements? What are your science requirements? Okay, what constraints or limits are there on your project and that have to be taken into account? Do you have a finite cost associated with it? We've already identified that your time is constrained. There might be other ones in too. So this effort goes hand in hand with the development of your system requirements. So I had mentioned earlier that the primary measures of your project are in terms of cost, schedule, and performance. It's usually very difficult to enhance or optimize all of these at the same time. There's this old adage, better, faster, cheaper. You know, at one point there was a NASA administrator who said that everything in NASA has got to be better, faster, cheaper. Well, the reality is pick two. All right, you really are almost impossible to be able to optimize all three of these. You can make things go faster or better, but not necessarily cheaper. Or you can have things faster and cheaper, but it won't be better. All right, so you really need to understand what your priorities are going to be in a project. So, are you constrained in terms of a schedule? Are you allowed to enhance some aspect of the project? Can you exceed some aspect of the project? These are things that you need to determine on these things. So, for example, you already know, and I've said it several times, that your schedule is constrained in terms of time. You have a fixed delivery of your payload. Well, if your faculty advisor allows, you can have infinite money. So you can go and you can buy whatever it is that you need in order to make that schedule. Or, for example, you've got your whole university available to help you with this project. So you can have hundreds and hundreds of people working on your project, all right, in order to make things go better or faster. So you need to determine just exactly what those limits are and which things that you can and cannot exceed. All right. These priorities always have to be reviewed as you go through the project because they will change as it happens. You may start off with a lot of money being available, but you're going to spend that up. So your pool of money is going to decrease. So you need to make certain that you can still fit within those constraints at any point along your project. Right. So organizing your tasks. So this is basically trying to organize your task as either in terms of a deliverable or a phase. So a deliverable, these are things where you've got a particular item that you can hand off to another a project or complete. For example, building a dam, a hydroelectric dam. That's a very concrete thing. You eventually deliver that dam, and there's concrete deliverables, within that project for things like the generators and the pilings and the foundation and other kinds of things. So there are a number of very hard deliverables that go into those things. So now your task definitions would then break down into sub-deliverables and then further deliverables underneath that until you finally get down to your work packages. So this kind of a thing or this kind of an organization can be highly parallel. And so you can run this in a fairly efficient thing, fairly efficient process, because you know exactly what it is that you're going to have to do at any given time. Another way that you organize or that projects might need to be organized is by phases or by processes. This can be a little bit more amorphous because the project could evolve over time, and whatever is happening in one phase affects what is required out of the subsequent phase. So you don't necessarily know exactly what your deliverables are at any given time, or exactly what it is that you need to accomplish until you finish one phase. So this kind of an organization might need to be much more sequential, right? Now, in fact, most aerospace projects are actually a combination of the two. Um, your many aerospace projects are unique, and so consequently are dependent upon innovations as you go through phases. But you produce tangible results like a scientific instrument or a spacecraft or a rocket engine or something like that. So many aerospace projects are basically a combination of both phases and deliverables. And your project is going to be a combination of that as well. Now I mentioned WBS. So what is that? Well, there's different organizations have different definitions of what these things, but there's common aspects of both of these things. So the NASA definition of a WBS is that it's a family tree subdivision of effort to achieve an end objective. And by that, they're saying that you you start with your end objective required and subsequently subdividing it into manageable components in terms of size and complexity. All right, the product or task oriented and should be included in all effort necessary to achieve the end objective. Okay, so that's a WBS is basically what they're saying is that your highest level are sort of the final products that you end up with, i.e. payload. All right, now underneath payload, you would have, power system, sensor system, control system. We talked about these things before, and then underneath each one of those is another set of subsystems. All right, so that's sort of what they're talking about. Now, the military handbook has a similar kind of definition of what a WBS is. So you can look through a variety of those lookups if you're really interested in definitions of WBSs. Now, why would you want to use this tool? All right, and there's several reasons why. Probably one of the more important reasons is that the WBS helps you identify if your project has every requirement accounted for and whether or not you have all of the items that you need to complete the project identified. So those are probably the two most important items of why you would use a WBS. It also helps you determine the relationship between tasks, helps you organize responsibility and authority. You can use it to estimate your cost and schedule, and you can track and monitor progress throughout your project by determining how many of these WBS elements have been completed and are you on time for completing it up to that level. So there's a number of reasons why you would want to use this. So I had mentioned that a WBS is a hierarchical structure. Well, the figure over here sort of shows what I mean by that. So the most general units are at the highest task. So here I've got 1.0 major task A, 2.0 major task B, 3.0 major task C. Then there's a tree structure for the subtasks. So underneath major task A, I've got 1.1 subtask A, 1.2 subtask B. And underneath subtask B, I've got 1.2.1 subunit A and 1.2.2 subunit B. Okay, so that's a hierarchical. You keep on splitting your tasks up into lower levels in it. Now this figure shows is going down to like level 3. Most projects, it's very unlikely that you would need to split subunits below level 4. That gets level 4 really gets into the nitty gritty, as you'll see in a second here. So usually you don't need to go down that low, and sometimes even level 3 is sufficient, depending upon how complex your project is. Um, Notice that there is a way in which the identifier is constructed. So 1.2.1. I mean, that's general convention as to how you identify those numbers. Usually these WBS subunits are a deliverable of some kind, all right? Possibly something for exiting a phase, like an ICD document, or some test results, or your system requirements. They can also be concrete deliverables, like power system, a sensor circuit, a readout system, etc. The lowest level of your WBS is what is called a work package. That work package includes three things: a description of the work to be done, including a time schedule, the resources needed and the cost of that work, and the person responsible for assuring the work is completed. All right, multiple work packages are going to need for each low-level WBS unit, probably. And then if you roll up or sum all the work packages underneath a unit of a WBS, that gives you your total sort of cost and time estimate for the unit. So for example, here is a example WBS. It's incomplete, but is sort of similar to the system diagram that I was talking about the other day. So in fact, here's our highest level: a power system, flight control unit, data archive unit, data archive disk, auxiliary transmitter, blah blah blah. These are all the major entities making up this one system. And then underneath power system, there's a power source, the FCU supply, HD supply, et cetera, and then the CubeSat supply. And as we start defining what this CubeSat supply is in the power system, then we determine that, well, there has to be an interface to the power source, which is up here, okay? There is some control interface of this particular supply from the flight control unit, the FCU. There has to be DC to DC converters involved, and there has to be some monitoring interface that the flight control unit is doing. Remember that we define those in that system diagram. And then underneath the control interface, there's work packages which are involved. So establish control requirements, design the control interface, prototype and test design, complete design, implement and test design. And one of the things that I do want you to understand and take away from this is that if somebody were to tell you, okay, give me the cost and the time estimate for power system, just a power system, what that power system is. I want to know how long it's going to take you to do the power system, right? That's going to be really hard, right? However, if somebody says, establish the control requirements, how long is that going to take you? Well, probably off the top of your head right now, you can give me a reasonable estimate, probably less than 1 day for this kind of a thing. What about designing the control interface? All right, again, you can probably have a much better handle as to how long that would take, as well as prototype, test design, complete it. You can, these units, my point here is that these units are much easier to get a fairly accurate estimate as to how long and what it would be involved, and that's why this is done this way. So, figuring out your estimates for these things at your work package, or even above that, there's a certain number of steps that get involved with doing that. So you need your general project definition and your set of tasks, like your WBS. You can perform a rough cost and time estimate. Uh, then develop your detailed WBS and get a cost and time estimate for your individual lowest elements, your work packages, if you will. Roll that up and then compare that to your initial estimate. At that point, you should be able to reconcile any differences between your initial overall rough cost and time estimate and your roll up on that. If they are close to each other, then you're probably pretty good. If they're really far apart, you better understand what those differences are from. There's a bunch of factors that can affect how you do estimates. So first of all, is your task estimates and definitions complete, right? Have you basically identified all of these tasks and are these tasks all within your schedule? Um, Secondly, people do not work at 100% efficiency. There is a difference between calendar time and effort. All right, we'll talk a little bit more about this later. Your structure of your project, okay? A dedicated team is able to focus its effort more effectively than individual efforts. So having a team can help with effectively running your schedule. Padding is some of the worst things or the easiest things that can screw up your schedule. Whenever you are doing an estimate, do not pad. Do not use this for, do not add in, quote, contingency, unquote, to take into account things that you don't know about. All right. You use as accurate an estimate as you possibly can. If you start padding everything, all right, you're going to find that you can't accomplish the task, and that is basically going to drive you into making trade-offs that you don't need to do. What's the culture of the environment that you're working in? All right. Does your management team allow you to pad? All right, or do you or are they demanding accuracy in your estimates? So that the culture can affect how you do those estimates. And then downtime. There will be downtime. There are things that will happen when you can't work. If if a tool that you're using breaks down and it has to be fixed, that's downtime. If you got exams scheduled or midterms or whatever, you're obviously not going to be working on this project during that time. So there is downtime that can happen and will happen. There's some estimating techniques that that are useful to know about that can help you with some of these things. So first of all, scaling. So given the cost of some previous entity or previous project, you can scale from that known cost to estimate what you are. So for example, NASA is notorious for using spacecraft weight to estimate the total cost. So they basically say, okay, how much does a spacecraft weigh? All right, well, when I put in this particular factor, then that's what the estimated cost would be. Sometimes that works, sometimes that won't. It works for relatively limited spacecraft, which are dominated by, say, channels of electronics or something like that. But it doesn't really work very well for spacecraft or instruments which have a lot of dead or even active mass. Okay, so that's something to use with a grain of salt. Ratio. So that this is something where you can estimate for multiple entities of the same product. So if it takes, 1 day to build this particular sensor unit, then if you have 10 sensors, that'll take you 10 days. Or if you have 2 people, then it'll take you 5 days for those 2 people to do it. So you can do that ratio type thing. Also keep in mind that almost inevitably the first time that you do something, and I'm certain that you know this intrinsically, it's going to take a lot longer than the second time you do it. And obviously the second time you do it will take longer than the third time. So there is a learning curve. So you gradually learn how to be more efficient in accomplishing a task the more times you do the same task. All right. So that you can use for estimating how your time costs. And then the most accurate way of estimating is this WBS roll-up process that I've been talking about for a bit here. All right. When you do your estimates, all right, here's a couple of guidelines to keep in mind. You should, those estimates should be done by people most familiar with that task. Okay. If you can get several people that can do independent estimates, that's even better. And then whatever their variation is, you can use that to say, well, okay, so for risk assessment, this task may be vary from 1 day to 1.5 days, depending upon what these independent estimates are showing you. Try to keep those estimates independent. Doing estimates sort of as a group, you'll quickly come to a conclusion which may or may not be correct. All right, so try to keep your estimates independent and then come back as a group to compare what you do. Always, always, always assume normal conditions for your estimates. Don't assume that there's a hurricane on the horizon, all right? Or don't assume that your laboratory building is burning down, while you're trying to do for your estimates, or whatever it is that would be abnormal. Assume normal working conditions. Use consistent units. Don't change from dollars to pounds sterling, or from kilograms to feet, or a variety of different conflicting units. Kilograms to feet would be very conflicting. Always use consistent units when you're estimating your tasks. Do not include contingencies in your work package estimates. They should be normal time, exactly what you estimate it should be. Okay. Contingencies come out later when you're doing risk assessment. That's when you start worrying about the effect of abnormal conditions and contingencies, not when you're doing your initial estimate. Okay, so here's a whole example WBS cost roll up. So the lowest level here, as I show here, is this FCU control interface, and so I've given some times for each one of these things and some costs for these as to what is needed. And these are all these lower level are all dependent upon each other, so it's sequential. And so if you add up this time, you see that total time takes 14 days of person effort. And if you add up all those dollars, it's 970. Well, if you do that for each one of these things, then you get these times and dates. You add up all these, you get for the CubeSat supply 45 days and $2,450. You do that for the other higher level ones, and then eventually to your main units, and you end up with a total price of over $27,000 and 710 days. Okay, for one person doing these things, I guess. All right, so that's how you can do that time and cost estimate on these things.